The detonation over Nagasaki in 1945 contained a plutonium core weighing just 6.2 kilograms. Size-wise, it could easily fit inside a standard backpack. But to make that tiny ball release its energy, the US government had to build a terrifying industrial empire. 130,000 personnel, massive chemical factories, and a production complex at Oak Ridge that consumed a staggering amount of energy, ranking among the largest electrical power loads in the United States at the time. This technology isn't just a smart physics equation. It is a profound flex of an industrialized civilization. Now let's strip it all away. No factories. No Google. No YouTube tutorials. You wake up 10,000 years ago in a loincloth. Your only asset is a crude stone pickaxe. Your mission is to recreate the entire global supply chain to reach the apex of industrial engineering from absolute zero. And no, you can't just skip to the final part. If you try to smash a stone tool into a specialized mineral mountain, you won't get a successful reaction. You will just get a broken rock, severe elemental contamination, and a complete failure of the project before the intro of this video even ends. This is a brutal systematic breakdown of how raw matter is forced to evolve, and why your primitive stone pickaxe is the most important starting point in technological history. Your journey to becoming an industrial superpower begins with a fundamental law of nature. Earth's geology does not care about your dreams. If you fashion your pickaxe from common river stones, it will shatter instantly. You must specifically seek out high-purity quartz or flint to achieve a Mohs hardness rating approaching 7. Even then, this tool is brittle and will degrade rapidly under continuous impact. Therefore, your stone tool has one unglamorous purpose right now: mining surface-level iron ore and coal. But congratulations, you dug up some red rocks. Now what? The brutal reality of physics is thermodynamics. A standard open campfire can technically reach high temperatures in its core, but the heat is scattered. It lacks forced airflow, and it completely lacks a reducing environment. If you throw your iron ore into a regular campfire, you don't get molten metal. You just get a very hot, useless red rock that mocks your lack of technological progress. To strip oxygen from iron oxide and reduce it into metallic iron, you have to build an enclosed clay furnace, fuel it with coal, and craft traditional leather bellows to force a continuous stream of oxygen into the chamber, raising the localized heat to a sustained 200 C. At this temperature, the iron does not melt completely, but rather sinters and turns into a solid, spongy mass of raw iron dross called a bloom. By pulling this glowing semi-solid mass out and hammering the absolute hell out of it, you squeeze out the liquid slag and impurities, forging your first metallic tool. If your stone pickaxe didn't spend days doing backbreaking labor to mine that specific pile of coal and ore, this forge stays cold. But because you survived the grind, your stone tool has officially cloned itself into a superior version with vastly greater durability. The iron pickaxe, the Stone Age, is officially dead. You are now a Tier 1 civilization. But muscle power alone cannot build advanced machinery. For that, you need to stop lifting heavy rocks and start learning math. With your new iron tools, your mining capabilities expand significantly. But you aren't digging for rare elements yet. You are digging deeper for more coal and copper. As your mine shafts descend into the earth, you hit a catastrophic bottleneck: water. The water table floods your shafts, completely shutting down production. Sucking millions of gallons of water out of a dark hole requires continuous energy. Over centuries, humanity relied on primitive water wheels and animal-driven mechanical pumps, but deep earth mining requires something revolutionary. You are forced to transition into the age of steam, culminating in the Newcomen steam engine. You use your iron tools to forge a giant piston, a boiler, and a condensation mechanism. By burning the coal you mine to boil water, you create a vacuum that drives a massive mechanical pump. If your iron tools didn't mine the coal to fuel the steam engine, your mines remain flooded, and your technological evolution drowns. But because they did, you have successfully converted raw fossil energy into continuous mechanical force. You have just unlocked machine tools. By using steam power to run primitive lathes and milling machines, you can finally cut metal with sub-millimeter precision, a level of consistency completely impossible by hand. This precision is non-negotiable, because high-level engineering requires perfectly shaped, symmetrical components. If your measurements are off by even a fraction of a millimeter, your entire system will misfire and turn into a very expensive non-functional ornament. Now that you have heavy machinery running on steam, your automated drills can finally breach the deep geological strata to harvest two specific minerals, pitch-blended the primary ore of uranium and fluorite. But nature is highly uncooperative. Natural uranium consists of 99.3% uranium-238, which is useless as the primary fissile core material. You need uranium-235, which makes up a miserable 0.7% of the ore. Historically, separating these identical isotopes required monumental factories utilizing gaseous diffusion and electromagnetic separation, converting solid uranium into a highly corrosive gas called uranium hexafluoride. To make this gas, you must bake your mined fluorite with sulfuric acid to produce hydrofluoric acid. This acid is so aggressive it dissolves glass on contact. If your steam-powered machines didn't forge corrosion-resistant nickel-lined pipes and airtight valves, this gas will leak, ruin your equipment, and end the video early. Every single gear, valve, and drop of acid in this chemical plant exists only because your early iron tools built the machines that could refine them. However, the technology for the Nagasaki device requires a different path. Plutonium-239, an element that does not exist in practical amounts within Earth's crust. To create it, you do not need highly enriched uranium-235. Instead, you use your industrial infrastructure to construct a massive, specialized nuclear reactor using ultra-pure graphite as a moderator and pure water as a coolant. You feed raw, natural uranium directly into this reactor. As the atomic chain reaction stabilizes, the abundant uranium-238 isotopes absorb neutrons, gradually transforming into plutonium-239. Once the cycle is complete, you must submerge the highly radioactive fuel rods into massive chemical separation pools, using advanced acids to isolate the pure plutonium. If your previous chemical plants didn't achieve absolute isolation, the system will instantly fail and terminate the project. You are now at the end of the tech tree. The physics are ready, but the final assembly requires crossing the most difficult barrier of all: integration. To successfully trigger the device, the system requires extremely precise timing, advanced specialized electronics, high-purity metallurgy, and complex explosives engineering. Every single component required for this final phase, from the thousands of feet of high-purity copper wiring dug from the deep tunnels of your steam pump mines, to the specialized steel alloys and heavy tampers forged in your high-temperature blast furnaces, is a direct, unbroken descendant of the raw physical work done by that original stone tool. When the historical reality of this technology manifested in August 1945, the illusion of mechanical simplicity was shattered. The Japanese Empire possessed brilliant physicists who advanced the theoretical understanding of fission. Yet, Japan could not construct such a device. They lacked the massive uninterrupted power grids required to sustain production reactors and fuel the immense demands of isotope separation plants. They lacked the vast, undisturbed industrial sanctuaries to scale up chemical refinement, and they faced severe shortages of raw industrial copper and specialized steel. The Manhattan Project succeeded not because the physics theory was entirely exclusive, but because the United States possessed an unmatched, sprawling industrial supply chain capable of absorbing immense economic and material costs. However, the ultimate realization of this industrial ladder resulted in unprecedented devastation. The historical detonations in Hiroshima and Nagasaki demonstrated the terrifying cost of total war, inflicting immense human suffering, catastrophic loss of life, and generational trauma on hundreds of thousands of innocent civilians. This historical turning point forced humanity to confront a stark reality. The infinite acceleration of military technology leads only to mutual destruction. The true measure of a civilization's advancement is not its capacity to unleash atomic fire, but its collective wisdom to prevent it. True progress lies in the preservation of peace, cooperation, and the understanding that war ultimately yields no true victors, only profound shared tragedy. The reaction is simply the final, powerful release of energy that was locked away in the universe for billions of years. The genius wasn't just finding the formula. The genius was building the massive industrial ladder to reach it, and the very first rung of that ladder was a primitive tool smashing a rock against a cliffside. High-level technology, in its truest essence, is just a stone pickaxe evolved to its absolute ultimate limit, a tool designed to alter the very architecture of matter itself, serving as a permanent warning of why humanity must always choose the path of peace.